technical sessions will start today with 4 keynote speakers. Each keynote speech is around 25 minutes. And our first keynote speaker is Mr. Philip Baldry. His speech is entitled "The Green Age, What Does It Mean for Industry?"
Good afternoon. First, thank you to the Chamber of Mining Engineers and the Congress organisers for putting on such a great show. And I hear it's the most attended Imcet that has happened in the last 28 years, and it's fantastic to be part of that event. I am Philip Baldry, the Executive General Manager of RPM Global's advisory business. I'm based in Sydney in Australia, and I look after a team of 140 mining engineers, geologists, processing engineers and environmental scientists supporting the mining industry. I've spent the last 7 years working here in Turkey, supporting our Ankara office as we have grown and supported the mining industry locally. So today I want to talk about the green age. What does it mean for our industry? What is driving it and the opportunities for the world's mining industry to reset its reputation through supporting the green transition and the energy transition? I will touch on the Paris Agreement, the energy transition and why mining is critical to that transition, key battery and critical minerals, the China dominance in this space, and also the government investments that are going into the battery and critical mineral space. And I'll leave you with some thoughts on things that the industry can do and all of the stakeholders involved with mining can do to support this energy transition. The Paris Climate Agreement came into force in 2016 and has been ratified by 195 countries. Its main goal was to try and hold average global temperature increases to less than 2 degrees by 2050 and 1.5 degrees by 2030. This was going to be done to effectively enhance the world's resilience to climate change, but also it allowed for alignment of financing to be aimed at various activities and objectives that could be used to reduce the world's dependence on greenhouse gases, or certainly the reduction in the production of greenhouse gases. 2024 is a seminal year where all of the countries that are signatories are to report back to the organising committee on which concrete actions they have taken to actually enable a reduction in greenhouse gas emissions, which will enable the reduction in temperature or average global temperatures. If we look at the latest IPCC report, unfortunately the news is not great. The current projections based on the commitments that have been made are that, if you look at the red line on this graph, that with the implemented trends we will still see an increase in global temperature and certainly an increase in greenhouse gas emissions that are being produced. For the world to actually achieve the goals of the Paris Agreement, which is this reduction of less than 2 degrees by 2050 and less than 1.5 by 2030, we need to reduce our greenhouse gas emission by 50% in 2030. For that to happen, you need to actually decarbonise a lot of the industries that are part of this world. And that decarbonisation process requires an energy transition which goes across multiple fronts, which really impacts the mining industry. We're talking about renewed interest in nuclear energy, and we've certainly seen that around the world. We're talking about a worldwide transition away from fossil fuel. This is gas, oil and coal. And obviously as we move to renewable energy, an increased need for battery storage to actually make the renewable energy sustainable and available when there is no wind or when there is no sun. And ultimately, another key part of that energy transition is a move to electrification of our transportation and vehicles. The global energy transition investment under the Paris Agreement surpassed $1.1 trillion in 2022. If you can look at the graph at the bottom, you see that there's a significant acceleration in that investment. And that is as the world starts to align behind the Paris Agreement, the investment that has been promised is actually coming to fruition and being put into the ground. There's a forecast out there that basically says that for every year moving forward from now to achieve our goals by 2050, we need to invest around 5.5 to 6.4 trillion US dollars into renewable energy and energy transition activity. That's a 6-fold investment in this space. And if you think about it in mineral terms, considering we're all mining people here, it is a six-fold investment in the amount of metal that the world needs to produce for these key battery and critical minerals. And if you look at the graph at the bottom, one of the things that you can see is that the magenta line has been growing much quicker than everything else. And that magenta line is all about electrifying transportation. It's about moving away from internal combustion engines and moving into an electrical realm in terms of our transportation. And I'll talk a bit more about that later on. So when we talk about battery and critical minerals, which minerals are we talking about? We're basically talking about minerals that historically have not been produced in any great quantity, especially when we look at lithium, graphite, cobalt, nickel, manganese, and rare earths. To meet the targets of the 2030 and the 2050 energy transition, we're talking about having to produce 4,000% more lithium than what we are producing today. 2,500 more graphite, 2,000% more cobalt, so on and so forth. Rare earths, we're talking about almost a 500% increase. And even copper, which is a very small bar on this graph, will need to grow by about 30%. And anybody in this room that has built and commissioned a new copper mine knows that that is a very capital-intensive process that takes a very long time. So for us to meet the demands of this transition means that the mining industry needs to go and find these resources, needs to develop technology to both process and refine these minerals to an end product, like a precursor cathode active material, PCAM, or a cathode active material. And this will require significant investment and time, and we don't really have a lot of time. 2030 is basically 8 years away, and when you look at 2050, it's not that much further away. This is a great opportunity for governments, private enterprise, research universities to actually collaborate together to accelerate the development of technology and research to extract these minerals and to refine these minerals in an energy efficient, environmentally friendly way. And it's great to see there's a lot of activity in that space. Ultimately, the development of these projects cannot happen at the expense of growing social norms. And certainly social license to operate expectations are a must and are things that we must commit to as an industry if we want to actually reset the reputation of the mining industry in this space. There's a graph down here which shows some of the key aspects of that energy transition. We're talking about the move to nuclear and which minerals need to support that transition. An example, nuclear, obviously uranium and nickel. Electricity networks, you require more copper and aluminum, but electric vehicles require almost all of those minerals in greater quantities and greater importance than they ever have in the past. And again, these are the minerals that today we are not really producing in great quantities and certainly not in line with the forecasted demands beyond 2025 through to 2050. Looking a little bit at a snapshot of that energy transition and focusing on electric vehicles, what is driving that push towards electrification of transportation? And it is very much driven by governments. In the chart below, what I'm showing you are 22 countries that have actually committed to banning outright internal combustion engines by 2030, 35, 40 or 50, or at least making it very hard to purchase internal combustion engines within these countries. That alone will drive a significant amount of electric vehicle demand in the world. The 9 countries at the bottom in green have also made net zero pledges towards energy transition around EVs, which basically means that their existing baseline of internal combustion engines can only be replaced with electric vehicles. So that driver pushed by governments to actually see an electrification of transportation will mean that we're going to need a lot more minerals. I think the estimate that I saw for the EU was something like 30 million electric vehicles will be required by 2030 to meet their decarbonisation targets. If you look at an internal combustion engine, the graph at the top, you need 34 kilograms of battery and critical minerals in an internal combustion engine. Copper, manganese are the main minerals that go, critical minerals. If you move to an EV, you're talking about 207 kilograms per car of battery and critical minerals. We now need copper, lithium, nickel, manganese, cobalt, graphite, zinc, rare earths, and a myriad of other minerals to actually make an EV. Where those minerals come from and the forecasted demand for those minerals is significant, and what we're basically going to see is a huge increase in demand for those types of minerals into the next 5 years, and certainly as we move further away from today's reality. Before I move on to where do these minerals exist and where are they found, I just want you to take a couple of key points away. The main thing here is when we look at the minerals, they're not distributed everywhere in the world. Geology is not that nice. You don't see copper deposits in every country. You don't see nickel or lithium deposits in every country. And the challenge of the location of those mineral deposits, as well as where they are refined, is the real challenge for the mining industry. So copper today produced primarily out of Chile and Peru in the Atacama Desert. These are very large, low-grade porphyry deposits that have been in operations for eons. Also produced out of the DRC, and also a fairly good spread of copper deposits in the United States, Canada, Russia, Kazakhstan, and into China and Australia. So copper is reasonably well spread out around the world and easy enough to get forms. One is obviously as a hard rock spodumene deposit. There you are talking about Australia. Australia, I think, historically had 80% of the world's lithium spodumene resources. But you also see hard rock resources in Canada, the USA, and to a lesser extent China. You then have lithium brines, and these are salar evaporation brines that occur in Argentina and Chile, and also occur in China in the pre-Tibetan plateau. Interestingly, in the last 3 years, we have also started to see lithium brines being extracted from old salt domes, which is where oil and gas deposits used to occur. And this is where the diversification of resources for these deposits come from. You are looking at projects like the Vulcan project in Germany and a project in the USA that are actually extracting lithium brines from deep seeded salt domes and using new technology, direct lithium extraction, to recover those minerals. And it's these sorts of evolutions of sources of minerals that will actually enable us to meet the likely demand for these battery and critical minerals. Manganese. The Bushveld complex in South Africa is the biggest producer of manganese today. Gabon has an extension of that same complex. China, and as I see around the world, there are a number of manganese sources, including in Turkey. Nickel comes in two main forms, sulfide and laterite. In the sulfide space, Norilsk nickel is probably the biggest global sulfide deposit of nickel anywhere in the world. Australia, Canada, the United States all have significant deposits of nickel sulfide. Nickel laterite historically could not be used as a battery and electrical vehicle precursor because of the form it was. However, through high pressure acid leaching, you are now able to recover battery precursors out of nickel laterite deposits. And what you're seeing here is Indonesia and the Philippines. All of these tropical deposits are the leading countries for battery and critical minerals for nickel. Rare earths spread out across obviously Australia and the United States and Russia for heavy rare earths, and for light rare earths, Brazil and China. But the real challenge with rare earths is actually not where they are found as a resource, but actually where they are refined. And the biggest challenge for the industry and the supply chain is China's dominance as the refiner of battery and critical minerals. On this chart, you can see a reasonably diversified group on the left-hand side of metal producers, as I've shown in the map previously. But when you start to look at who actually processes and refines these minerals to an end product, China is a clear dominant force in that space. And a classic example is rare earths. 87% of the world's rare earths today, which are used in your phones, are used in your electric turbines, are used in your EV motors, is produced in China. The technology actually is French technology, which was developed in a processing plant in La Rochelle many, many years ago, was sold to the Chinese 15 years ago, and now the French have almost lost all of that knowledge. With all of the technology and all of the IP now sitting in China to process these minerals. This supply chain imbalance and the risk that it can present is what has woken up a lot of the world's governments to the need to actually develop their own domestic sources of battery and critical minerals, both the mining and the processing and refining of those minerals. And what we are seeing is a multi-generational investment, not just by governments, but also by car manufacturers, battery cell manufacturers, who are attempting to control their supply chain, who are now investing upstream into the mines and downstream into the processing plants and the refinery. So moving back to a vertically integrated world. The level of investment that governments are putting into battery and critical minerals is multi-generational. We have not seen as much money go into the mining space and the refining space than what we have seen in the last 3 years. You have the Inflation Reduction Act, which is $392 billion of investment in the US. You have the EU's Critical Raw Material Fund, which is $1 trillion fund aimed at actually enabling the development of the mining, the processing, the refining and the recycling of battery and critical minerals inside the EU. In Australia, we have a $2 billion critical mineral fund, which just doubled a couple of weeks ago. And over in Canada, they have introduced a critical mineral exploration tax credit to incentivise explorers to go and explore for these battery and critical minerals across Canada. And it's that level of activity that is actually required to enable this battery and critical mineral transition. The technology that is involved with extracting battery and critical minerals and refining battery and critical minerals is not the same as a flotation plant or a gold cyanide plant. It is complex, it is emerging, and it is not mature technology. And only with the support of governments and critical mineral funds can these projects actually come to fruition and become part of the supply chain. So that level of activity is certainly something that we're seeing around the world, and it's just interesting to see how that is helping develop projects that, in a traditional sense, if you had to rely on private financing and on lender finance from banks, would be very hard to secure. In terms of RPM, we're across over 100 of these types of projects all around the world. We actually work for the battery manufacturers and the car manufacturers, LG Energy, POSCO, Sumitomo, PowerCo, which is part of the VW group. We work for the banks that are investing in this space, so BNP, SocGen, ING, and we also work for the critical mineral funds, the government agencies that are lending money to these projects. And this view of the investors that are going into the battery and critical mineral space, as well as the new projects that are being developed, has given us some really interesting insight into what does it really take to really shift the dial in terms of the development of your own in-house domestic battery and critical mineral space. So here are a couple of thoughts that I want to leave you with. The first one is dust off your archives. Finding new sources of minerals, especially battery and critical minerals, through the use of emerging processing technology is still in its infancy. And it's amazing to see some of the new deposits that in the last 12 months have been discovered, where people started to look at old data. And I think Turkey has a fantastic opportunity with MTA. You have a huge wealth of geological knowledge sitting in archives in Ankara, which could actually be revisited and should be revisited to identify new sources of battery and critical minerals. A great example that I can use is the Iluka rare earth project in Australia. This is a rare earth refinery that is being built in Western Australia, and the actual resource that is being used is an old tailings dump. It was a low-grade, rutile mineral sand mine, and because the mineral sand was slightly radioactive after its processing, they actually stockpiled it. It was worth nothing for many, many, many years, actually decades. Now it is actually a $200 trillion reserve that is sitting on the ground, and the government of Australia has provided $1.4 billion to actually build a refinery to extract these minerals from what used to be a tailings dam. So how many tailings dam and how many waste dumps have been overlooked in Turkey that may actually contain battery and critical minerals? We need to invest in research and exploration. I listened to Professor Imcet talk about the importance of investing in research. It takes 10 years to bring new processing and refining technology to the market. It takes anywhere between 5 to 15 years to bring an exploration discovery to production through the permitting process. For that to happen, obviously, junior explorers need funding and new support from the government and from private enterprise to actually help them deliver on that research and exploration. We need to continue to invest in education. It's sad to say, I come from Australia, where I can tell you now there were 13 mining engineering graduates last year that came out of our 3 mining universities. If you look at the amount of people that are retiring from the industry, those people are not being replaced. And the development of new resources and this increasing need for development of battery and critical mineral projects will not happen if we have no new mining engineers, geologists, processing or mechanical engineers available to actually develop these projects. So there needs to be investment in education and encouragement for students coming out of high school to go into mining type university education. And it's great to see, certainly China and India are certainly still doing this. Turkey to a lesser extent, but Turkey still produces a significant amount of graduates, and something Turkey should be very proud of and should hold on to. And it was interesting, only on the weekend, the US has finally woken up to this fact and has actually put out a Mining School Act to help fund the mining schools of the US, because they realise that without graduates, they will not be a mining industry that can support the battery and critical mineral transition. It's a great time to be in mining. I mean, I look at my generation, you know, we're not a very big group that came through my generation, but this is probably the most exciting time for us to be in mining. It's an opportunity to reset our reputation as an industry around the world and to really make a stand as a key contributor to the world's carbon transition. However, to do this, we must do it sustainably. You know, there is no excuse today for developing projects without whole of stakeholder engagement. We need the community on board, you need the broader government and ministries on board, and you need the support of all of your investors if you are going to build a new mining project. There is no excuse for taking shortcuts, and the challenge for us is, with this rush to transition the world, is some of these projects will probably get pushed along faster than they should be. And we have to be very conscious of this, and we need to be proactive in ensuring that we are developing sustainable projects, both from a social point of view and from an environmental perspective. Otherwise, our reputation will remain, unfortunately, where it is today. And last but not least, partnerships. We need to identify the right partnerships to help develop these resources and the new technologies that go into this, and development of these mines, which are higher risk than traditional mines, will require government funding, will require university and research support, will require private equity as well as lender support to deliver on the transition. So on that note, thank you for your time. I hope you found some interesting points in here and some thoughts on how the Turkish mining industry and its stakeholders can actually contribute to the green age. If you have any questions, feel free to catch up with us at the booth. We have a booth just down in the main hall, and I look forward to hearing the rest of the presentations.
Thanks, Mr. Bordu, for the insightful speech. We just want to present you a certificate and a small gift for your contribution.
I'll go out this way.
We want to invite Professor Dr. Joe Koo for the speech entitled Dissolution of Gold in Imidazolium Cyanide Ionic Liquid.
Good afternoon, everyone. I'm Ko Jue from University of Science and Technology, Beijing, and I'm now working in Mineral Processing Department. On behalf of Professor Sun and all the other research members in our department, I'd like to express our thankful for the Congress to invite us to present our research work in this conference. Thank you very much. And also, I want to thank Professor Emery Altune for his help in the experimental design and paper writing in this research. And today's topic is about gold leaching. I picked this topic because Turkey has a large amount of gold resources and also have the cutting edge technology in gold ore beneficiation and gold leaching. Therefore, we are always trying to find the mature, mutual interesting area in gold beneficiation. So the topic is the dissolution of gold in imidazolium cyanide ionic liquid. And I expanded my topic a little bit, it including 3 parts. The first part is research background, and I want to explain why we are working on this topic. And the second part is the gold leaching in imidazole-based cyanide ionic liquids, which can be remembered briefly as IMCN. And the third part, I'm going to talking about the iodination gold leaching in imidazole-based dicyandiamide ionic liquids, which can be remembered as IMDIC for abbreviation. The first part is the research background. Cyanide leaching is a very mature technology and has a long history of research and application. And more than 85% of gold around the world are produced by cyanide leaching because it's simple and easy to control. It has high gold leaching efficiency and low costs. However, the cyanide has extreme toxicity. Therefore, in 2016, cyanide leaching residue and tailings and cyanide-containing water treatment sludge have been listed as a national hazardous solid waste in mainland China. Therefore, all the gold mines in China has to thoroughly treat all these hazardous solid waste, which brings a large amount of cost burden for lots of companies. Therefore, the development and application of some high efficiency and low toxicity or non-toxicity reagents or lixiviant became an urgent requirement for lots of gold companies. And that's why we are working on this non-cyanide leaching topic for a while. For non-cyanide leaching, actually, it also has a long history. For example, the halogen gold leaching starts from the earlier 20th century, and after that, thiosulfate leaching, thiourea, polysulfide, and lime sulfur, and alkaline sulfite, which are considered as the sulfur-containing lixiviants, are all started the research and the application, and in which the thiosulfide is considered as the promising lixiviant for gold leaching, which can partially replace the cyanide. So all these low toxicity lixiviant can be roughly divided into two groups. One group is the reagents with cyanogen, such as potassium thiosulfate, sodium dicyanide, and potassium ferricyanide, And these reagents are all proved to have good gold leaching probability. And there are also some literatures we have published for the research of these reagents. And the other group, without cyanogen, such as halogen leaching, thiosulfate, thiourean polysulfide, and amino acid. For halogen, since it also has a long history of research, people find that chlorine, bromine, and iodine has a strong bond with gold. And actually, the leaching rate sometimes is much higher than cyanide. However, there are some issues in the application of these halogen reagents, and I'm going to talk about it later in the third part. Therefore, it haven't been widely used in gold leaching. In China, there are lots of companies start to prepare these kind of environmentally friendly gold leaching reagents. Here I listed some, like the top 10 companies. For example, the first one, Jinshan, which is from the Guangxi province. According to the literature and the patent report, the bulk component of Jinshan is a mixture. It's a mixture of carbonized sodium cyanate and alkaline thioureum. And also we have some other types of reagents. Here we have the manufacturing, some photos for manufacturing and their products. Some of them did have some good effects in gold leaching. And in our research, we are always trying to find some reagents that can provide a stable chemical condition for gold leaching. And ionic liquids can provide a very good leaching performance. Ionic liquids is actually a kind of ionic compound with organic cations and organic anions. Since these cations and anions are quite big, so it's the pure component but with a very low melting point. And therefore, this kind of compound are liquid at the room temperature. There are lots of advantages of this kind of liquid. For example, it has negligible vapor pressure, it has wide electrochemical window, and high thermal and chemical stability, and environmental friendly, and also recyclability. And these physical and chemical properties are exactly what we are looking for in the gold leaching, especially the low toxicity leaching. And these ionic liquids are also widely used in hydrometallurgy process, such as metal leaching, electrodeposition, extraction, and separation. So in our experiments, we've tried lots of different types of cations, and we find that imidazolium has a very good performance and quite stable chemical property. So we pick imidazole as the cation. For anion, we've also tried different types of anions, and we'll talk about it later. There are also some references and literatures reported about the gold leaching performance of ionic liquid. For example, we have this paper from hydrometallurgy, can use it to dissolve the gold with strong oxidation and coordination capability. And also, the ionic liquids can be used as solvent. For example, for thiourean gold leaching, we can use the limidazole-based ionic liquid as solvent, but not use water, without water in this whole process. And it shows the very good selectivity of in between different metals. For example, the gold, copper, zinc, lead, or iron. And our research is trying to apply the ionic ion liquids in the leaching of e-waste, electronic waste, such as CPU from the dumped computer or a cell phone. And we try to see if this ionic liquid has the better selectivity in between different metals. And our research is supported by National Science Foundation of China. Now let's take a look at the part 2, the gold leaching in imidazole-based cyanide ionic liquid, MCN. So first of all, I'd like to introduce the synthesized method of ionic liquids. There are 2 steps. The first step is quaternary, to synthesize a quaternary ammonium halide. It's a kind of salt. And with the help of the salt, it's like the middle product, we can do anion replacement reaction and to get the ionic liquids with the certain cation and anions we need in our tests. And we got 2 products. One is IMCN, the left one, and the other one is, doesn't work. And the other one is IMDICY, which is known as IMDICY. MCN and MDICY. These are the 2 ionic liquid we used in the experiments. And we have tested the thermal stability of these 2 ionic liquids. And it turns out that these 2 products has very good thermal stability under the temperature, below the temperature of 100 degrees Celsius, which is quite well because most of the gold leaching process is, the temperature is not higher than 100 degrees Celsius. Therefore, we can adjust the temperature to the certain degree that is suitable for the gold leaching and without change the chemical property of the solvent. And for electrochemical stability, and we've tested the electrochemical window of these 2 products, and they all show a very wide window, which prove the stability of these 2 ionic liquid. And these are the leaching material we've used in this experiment. We have the different types of CPU pins, and we gather them together, melted at 250 degrees Celsius, to separate the metal with the plastic base. And we have this metal product, which contain about 86% of copper, 4% of nickel, and with some lead and iron, and 0.34% of gold. And these are some SEM an EDS analysis of the CPU pins. We've tried the MCN to see if it can have a good performance in the gold leaching with the CPU pin. And here we tried 4 different solvents. We tried different content, different temperature, and a different storing time. And it shows us that the high content of MCN might result in the high viscosity of the system. The high viscosity will decrease the leaching rate. Therefore, the better content for MCN in leaching is about 20%. And also we've tried about the temperature. Increasing temperature has a good help with the gold leaching, and it turns out that 60 degrees Celsius is much better. Therefore, it can help to increase the leaching rate. Also, this is the surface of the e-waste before and after the gold leaching with ionic liquid. And we can see before the leaching, it is quite smooth, the surface, but after leaching, it became rougher, and the gold coating are all diluted in the liquid. And this is the XPS spectrum of the leaching residue. And here we can see that the gold are oxidized to gold plus and coordinate with the cationic imidazole ring. And also we found the nitrogen and carbon on the surface of residue. And this is NMR spectrum and ESIMS spectrum of the pregnant solution. And here we can see that the chemical shift of carbon peak near 165 ppm is consistent with a certain structure. This structure is called a nitrogen heterocyclic carbene gold complex, which is mostly like that, with the gold in the middle, and it connected to the structures of ionic liquid. And the third part is about iodination gold leaching in Imcet. Iodination leaching is already demonstrated to have a good performance in gold leaching with both raw ore and the e-wastes, and some other materials contain gold and some precious metals, because the iodination method has a fast leaching rate and has good effect because of the strong bond between the iodine and gold. However, it cannot be widely used because the high cost of iodine. This is the result of volatilization loss of the reagents. Therefore, to get the better performance, we have to control the temperature precisely and add the gas collection device to recover a certain amount of iodine. And also in this process, we need to add a large amount of potassium iodide to dissolve the iodine in the liquid. Therefore, it has large consumption of potassium iodide. According to the literature, the iodine leaching has a very good performance in different kinds of raw materials. For example, for oxidized gold ores, under the room temperature, the leaching rate can reach to 89% within 24 hours. For flotation gold concentrates, which are mainly sulfide, the leaching rate can reach to higher than 90% within 4 hours under the room temperature, which is quite similar with cyanide leaching. And for e-waste, since the impurity is quite low, this leaching rate can reach to 95% within 3 hours. So if we can apply the iodine in the gold leaching, that will be a very promising methods. The only problem is how can we prevent the loss of the iodine in this whole process? Is there any possible that we can reuse the iodine in this process? So this is the new method we've designed in our research. First of all, we don't use water. We use Imcet as the solution, as the solvent. We dissolute the iodine in the Imcet and to prepare the gold leaching lixiviant. And during the gold leaching, we collect the pregnant solution. And to further recover the gold from pregnant solution, we use electrode deposition. We use carbon felt to deposit the gold on the surface. And in this table, we compared the parameters of the water solvent gold leaching and the ionic liquids solvent gold leaching. For water solvent, the volatilization loss of iodine is quite high, but for Imcet, the iodine recovery rate can be reached to 80%. And for solvent consumption, for water solvent, it cannot reuse. But for Imcet, we can reuse it by reuse the analyte. The rate of recovery also reached to higher than 80%. And for electrode deposition of gold, in the water, since it has large amount of hydrogen, the hydrogen evolution reaction becomes the main competition reaction for gold deposition, and the current efficiency is quite low. If we use ionic liquid, since there's no hydrogen in it, or less hydrogen, so it has higher current efficiency. Therefore, we can use electrode deposition to recover gold from pregnant solution. And this figure shows us how stable the iodine in the Imcet. So the first row are the cap of the container at the very beginning. All these caps are white with no color on it. After 12 hours, we can see in the water solution, the cap of the container turning into the dark red, which tells us that might cause the loss of the iodine. And in the other three caps are the ionic liquid solvent. And we can see the color is very light and almost no iodine evaporated in the ionic liquid. And we also do the electrostatic potential energy calculation, and we find that the halogen bonding is very strong. It's the main driving force for the migration of iodine into the ionic liquid. And also the solvent-induced effort can furtherly increase the solubility of iodine. Okay, and in this figure, it is a comparison of the water solvent iodine gold leaching and the MDIC solvent leaching. And to get the same leaching rate, above 90%, for the water solution, in the water solution, the potassium iodine concentrate is 10 times of the iodine. But for the MDIC, no potassium iodine is needed in this process. So the influence of iodine dosage, leaching temperature, and time are all shown in this figure. And also, this is the comparison of the leaching rate of different metals, including gold, copper, nickel, lead, and iron. And here we can see the gold has the highest leaching rate of 93%. Copper is 20%. It shows a better selectivity in the leaching process. And this is also the comparison of different iodine dosage, time, and temperature. And I'm going to skip this page. The best condition is right here. And also in the leaching residue, we find the nitrogen and iodine elements on the surface. And the gold is oxidized in this whole process into the gold plus. And this is a very interesting result. We use the ESIMS spectrum to test the pregnant solution. And we can see that before and after leaching, the cations in this pregnant solution has no change, which means the imidazole doesn't change at all in the whole process. We can reuse it and recycle it in our process. And in the anion, for the anions, we find 4 new anions in the pregnant solution. The structures are more like in this picture, and we can find the gold dicy complex, gold iodide dicy complex, and gold iodide complex. And we also calculate the contacts of different complexes in this whole pregnant solution. And for furtherly recover the gold from the pregnant solution, we did the electrode deposition experiments. And we tested the efficiency, current efficiency, and specific energy value as a function of potential, temperature, and stirring speed. And here we found that the carbon felt has a better performance than titanium plate. And from this SEMEDS image, we can see a lot of gold deposit on the surface of carbon felt because it provides a large specific surface area. And we also detected a little amount of copper deposit on the surface too. Some of are like the copper metal, some are copper oxide. So in the future, we will try to minimize the copper leaching rate to decrease the copper content on the carbon felt. And this is the rate of recycle of all these materials. Our main goal is to recycle the iodine, to recycle the lixiviant, recycle the MDIC. So the maximum recovery rate of iodine can reach to 85%. And by reintroduce the analyte with addition of 0.2% of iodine back to the leaching operation, the leaching rate of gold and the electrodeposition efficiency can reach to 93% and 95% respectively. So it shows a very good performance and no extra iodine needed in this whole process. Although the Imcet is a bit expensive, but we can reuse it for lots of times. In this experiment, we reuse it for 4 times, and the leaching efficiency are quite stable. And here are some publications. We published some papers about our research work. And I still want to take a few minutes to introduce our new journal. It's called Green and Smart Mining Engineering, GSMI. It's a new international journal in mining and mineral processing, which is sponsored by USTB. And it is free, open access and peer-reviewed journal. And with the co-editors from Professor Cai Meifeng and Professor Emmanuel Detournay from University of Minnesota. And we are looking forward to have this journal indexed by SCIE within 2 years, like before 2025. So welcome, and we hope the inventors all around the world will interested in this journal and submit your research work to this journal. And thank you very much for having us here. And welcome to China. Thank you.
Dr. Ku, thanks again for the informative speech. We want to present you a certificate for your contribution and a couple of small gifts. The third invited speech will be given by Professor Bernd Klein. We invite him to the stage. And the title of his presentation is Sensor-Based Bulk Ore Sorting of Precious Metal Ores.
Okay. There's no presentation here. Okay. I just want to make sure I know how to work this. No? Oh, yeah. Okay, good. Okay, good afternoon. It's a pleasure to be here in Antalya, Turkey. I'd like to thank Imcet for the invitation, and particularly Professor Emre Altun, my old friend. Today I'm going to talk about sensor-based bulk ore sorting of precious metal ores. In the last Imcet conference that I attended in 2018, I also talked about bulk ore sorting. And there have been a lot of advances since that time. But one of the challenges is related to, can we use, for the mineral resources industry? Not only do we have a strong demand for particular critical minerals over the next 20 plus years that we are going to have a tough time to achieve, but also, I find that in recent years, the industry has been more receptive to innovation and technology than they had been for a long time. They're more willing to accept new technologies. And bulk ore sorting is such a technology. It's relatively recent, but everybody knows the expression in mining. Everyone wants to be first to be second. And now there are a lot of firsts, so there's an opportunity for a lot of seconds to understand the value of the technology. I'd like to also recognize my co-authors, Ganzhuang Li, Mahir Setin, and Yang Zhu. Okay, so in my talk today, I'm going to give a bit of an introduction because I'm not sure how widely known this topic of bulk ore sorting is, just to make sure that people know where we stand with it. Talk about some of the technologies. I'm going to talk a little bit about sortability. Not every ore is sortable. On the right of this slide, you can see a process for assessing if a material or an ore is sortable. You first have to have heterogeneity. If there's no variability in your material, you're not going to be able to separate anything. Then you have to decide if there is variability, is there a sensor that can detect the difference between something that's valuable and something that's not valuable? If you tick the first two boxes, then you can say, well, what kind of sorting machine or system are we looking at? Is it going to be mounted on a conveyor belt? Is it going to be put on a shovel? Where in the circuit is it going to be located? What are the implications to material handling? So there are various factors that you have to think about. And once you have all of that information, you tick those three boxes and you can say, okay, now economically does it make sense? Okay, so those are all key. So I'm going to talk a little bit about heterogeneity, and then I'm going to focus on particularly bulk ore sorting related to precious metal ores. Some of the opportunities and challenges, how we can detect elements like gold that's at parts per million levels indirectly using various options, and compare the available main sensors that are being used today for bulk ore sorting before I make my conclusions. Okay, so I mentioned heterogeneity. If there is no variability in your ore, there's no opportunity in order to exploit. So historically, we have used geological models to develop block models, and based on those block models, we develop a mine plan. We designate blocks of ore as either ore or other blocks as waste. And so when we mine them, we send the waste to the waste dump and we send the ore to the concentrator. And then we crush and blast, we blast and truck the material to the processing plant. And what do we do at the processing plant? We grind it and try to liberate the valuable minerals to create heterogeneity so that we can separate them. Okay? However, we know that as we are building bigger and bigger mines, these block models they don't have the resolution of selective mining to know if within a block there is some high-grade material or some low-grade waste. We try our best with the grade control engineers who might look at the blast hole information to indicate whether the material should be sent to a process plant or a waste dump. But still, it's a qualitative assessment. So we know that there's an opportunity to do better than we're presently doing. Many of you are mining engineers. You know about selective mining. And you know that in bulk mining methods, we're not very selective. Another important factor is on the bottom right here is that I use this term heterogeneity, and that means variability. How much variability? Is it a low amount of variability or a high amount of variability? The higher the amount of variability, the greater the opportunity for sensor-based sorting. And as we start at larger scales in terms of meters, of cubic meters of volume, there may be a lower degree of heterogeneity, but as we go to smaller and smaller unit sizes, we see that there is an opportunity for heterogeneity. Such as the picture of the mining block in the top corner there. That mining block might have an average grade that's either ore or waste, but we know that at a smaller scale and with higher resolution, there's high-grade material and low-grade material within that. So there's opportunities for bulk ore sorting down to a particular unit size. That depends on the technology. It might be a few cubic meters of material at the smallest size. And if we reduce the particle size even further, we get into rocks. And if there's heterogeneity between rocks containing valuable metal and those that do not contain valuable metal, we can do particle sorting. And then after grinding, we create heterogeneity and we use flotation. So sensor-based bulk ore sorting, it's been implemented at various locations in the material handling system, starting by putting sensors on shovels and buckets. We can also, there are systems as well for mounting sensors above trucks as they drive through. It will indicate something about the quality of the material in the truck. And there are several systems where sensors are mounted on conveyor belts in order to monitor the quality of the material. Most of these applications have been based on grade. I should say that there's other opportunities besides grade. There could be opportunities, I work on an area called real-time geometallurgy. So we all know the importance of geometallurgy. We try to allocate geometallurgical domains within a deposit so we know if it's hard, if it's high in arsenic, so we can blend it, so we can do different things. So beyond grade focus, there are other opportunities that we can use these sensors for. And this all relates to this interesting time where the mining companies are focused on intelligent mining, digitization, and these sensors are creating two types of sensors that are being applied. And this is not a thorough list, but this is some of the types of sensors and the companies that are producing sensors for bulk ore sorting. MineSense is a company that I'm actually a co-founder of, based in Vancouver. The MineSense was created out of my research at UBC. And we put sensors on shovels, and I'm going to show you a little bit. We also put them on conveyor belts. Rados have done a very good job of putting XRF sensors on belts for diversion of material. IMA Engineering, they have a fast conveyor analyzer that uses XRF, so there are a few companies that are presently using X-ray fluorescence. Prompt gamma neutron activation analysis, it can detect multiple elements, including light elements and elements like sulfur, which XRF cannot do in a bulk sorting application. There are companies like Scantech, Thermo Fisher Scientific, who are focusing on developing belt sensing systems using PGNAA. And one very interesting one that I find it interesting was developed by CSIRO in Australia, marketed by Nextdoor, and they use magnetic resonance. Same thing that we do to scan our brains for tumors. They use to scan for particular minerals, and they're very good at certain minerals like chalcopyrite. And for me, it's fascinating. I've met with them and talked to them. And they've initially mounted on conveyor belts, but they're also starting to look at mounting such on a sensing portal where trucks can drive through to analyze the grade. Okay, so here are some examples of where at least sensor systems have been included onto bulk streams. The Newcrest, or Newmont, I'm not sure, is it Newcrest still? Their Katy East mine is a copper gold. And they have a PGNAA system and a magnetic resonance system on their conveyor that leaves the underground mine after crushing. And for a mine like this, gold is just as important as copper. So if you sort just based on copper, that means losing gold, it's not going to be of any value. The New Afton gold mine in Canada, where they use PGNAA, also copper gold. Gold is a very valuable component of the ore. Sepon in Laos, copper gold. So you can see in many of these cases, we have ores that have not only one element that's of value like copper, but a second element such as gold, which might be of equal or even higher value. And there's one example of a platinum element mounted PGNAA and XRF system. So, just going to show you a few of the systems. These are some of the more common conveyor systems. PG&AA is on your left. You can see how it just fits over a conveyor belt. It uses a gamma radiation source, and there are gamma rays emitted as the material flows through the bed, and the emitted gamma rays are a detector helps to identify what the specific elements are and what the concentrations are. Magnetic resonance, I mentioned, uses the MRI system. Very good for specific minerals, but not all minerals. For example, it can measure chalcopyrite, but it can't measure bornite. So if you have a mixture of the two, it may not be sufficient to tell you what's the copper grade of the material that you're trying to separate. And XRF, there was a few examples that I listed before. And so these are all belt mounted. So you mount them on a belt, and then you need some type of a diverter system that will allow you to divert high-grade, low-grade waste in order to achieve your sorting. The MindSense, they were the first to install XRF sensors on a shovel. And as the material is being collected, it's being scanned. And so there's a flow of material into the shovel that's being scanned, so it's getting a sampling of that flow. And after it's being scanned, it's quite quick. The operator, in the shovel operator, he has what looks like a little iPad, and it indicates what's the grade. Is it above threshold? Is it below threshold? Generally, they use these for sorting at the truck scale. So if it takes 3 or 4 shovels to fill a truck, they accumulate the average grade of the shovels in order to make a decision, where does this truck go? They haven't been able to justify having 2 trucks next to a shovel because fleet management would find that very inefficient use of trucks. So they obtain the information very quickly and they can divert it. There's a link to a video here, but I'm not going to show it for the sake of time, but it shows how fast this is. And it's also pretty accurate. It's accurate to within about plus or minus 0.03 or 0.04% copper. So that means if you're picking up material that's got 0.3 copper, it will read between 0.27 and 0.33. So when I first saw that, I was surprised. I thought, okay, MindSense has a product. Okay. And it can be mounted on large shovels, 75-ton shovels, even 100-ton shovels. So it allows you to make decisions at that scale. When the first mining operation to use the ShovelSense system tested it, they operated for about 6 months where they only used it on waste. They didn't want to risk losing ore. And after 6 months of gaining confidence in the use of this technology on trying to recover ore from waste, they then made the decision, okay, let's try it on ore blocks to see if we can reject some waste. And so now their main benefits are to recover ore from waste as well as to reject waste from ore. And so there are a number of benefits to that. MindSense is also yet, at this present time, putting these XRF sensors on LHDs for underground operations. So, bulk ore sorting opportunities. It allows selective mining while applying bulk mining methods, so low-cost mining methods. I know that for some of the gold mines and silver mines that I've conducted projects for, they're concerned that they're going to lose some value. And so they really are focusing on more selective mining methods in order to follow the gold. A technology like this may allow them to consider lower cost mining methods that are less selective and maintain recoveries through some type of sensing system. As I said, recovery of ore from waste, rejection of waste from ore, diversion to stockpiles, you can make all those decisions. The net effect is potentially an increased grade to the processing plant, an improved metallurgical recovery, increased metal production at a fixed processing rate, Definitely increased resource utilization. You're not sending valuable material to the waste dump, so you're using your resource and getting as much out of it as you can. And there are a number of other contributions, like decreased water consumption per ton of product produced. Limitations, when you're doing bulk ore sorting, heterogeneity is greatest in situ, within the deposit, okay? As soon as you blast it and start to handle it, you're starting to mix it. And then if you put it through a crusher and a stockpile, you may have lost the opportunity. So we need to do it as close to the face as possible. The scale of the sorting unit, I showed you shovel systems, conveyor belt systems, depending on the sensor, may have a certain resolution of, might be 100 tons, might be 200 tons, depending on how fast that sensor works. But with respect to precious metals, the detection limits are the critical factor. None of these sensors can actually detect metals at the parts per million level. So when we talk about precious metals, generally they have a high degree of heterogeneity, but they occur at low concentrations, like parts per million, that are below the detection limits of the three sensors that I've referred to you today. They have the opportunity to be used for grade control, but in the case of precious metals, there are many precious metal ores that contain refractory components that need to be treated in a certain way, and there are also precious metal ores that will divert to grinding and tank leaching or to heap leaching. So there's an opportunity to apply it there as well. So how do we try to classify materials or ores that contain precious metals? The first option is just to try to find a proxy. What sensor do you have, and can that sensor detect something that relates to the gold content? I showed you examples of copper gold ores, and in some cases, copper is a great proxy for the gold, and wherever the copper goes, the gold goes, but not always, particularly when you have issues like nugget effects. The sensors generate a spectrum of information, several elements. So you can apply simple multivariable linear regression to create a model that accepts the whole range of element concentrations that you get out of the sensor, and you develop an algorithm that can be used to convert that to a gold grade. However, in this age, machine learning is being applied increasingly to a lot of different things, and there's an opportunity to improve classification through machine learning algorithms. And another option is to look at combining the strengths of more than one sensor. Okay, proxies, I basically described it. In some cases, there's an excellent correlation for copper gold ores between copper and gold, and in other cases there is not. And if there is, well, then you can use the copper content as the basis for the sorting, and if you're fortunate, the gold will follow it. This was an example that was conducted for the Katy East panel cave mine, and without going into too much detail, the issue here was that they contained both chalcopyrite and bornite, and at depth there was varying ratios of gold to copper. It wasn't constant. As well, it's a fairly homogeneous deposit. So if we sorted based on copper, we were able to get quite low reject grades of copper, but not so effective for gold. So depending on which cave they are operating, there's three listed here, PC1, PC2 West, PC2 East, we got varying results. Upgrading, a small amount, except for PC2 East, had more significant upgrading. And the mass rejection, PC1, PC2 West, probably not good cases for bulk ore sorting, but PC2 East, where you can reject more than 10% of the material, it might have a significant impact. So it's not a really glowing example, but it was reality. So, Multivariable regression, as mentioned, you can develop models that incorporate all of the information from the sensor, whether it's XRF or PG&AA, and probably magnetic resonance if you can identify more than one mineral. And you can put that into a simple model as shown on the bottom there in order to come up with a predictor for gold grade. Again, this is not a stellar example. The R-squared was only 0.68 here. Machine learning, we've been increasingly applying machine learning. There are a number of different methods. If you have a small data set to try to calibrate your system, logistics regression, support vector, generally a robust, generalizable ability of these methods, and their calculation speeds are high. For large data sets, there's a number of other methods that we have been applying. But in this case, we're not predicting the grade, we're classifying the material. So we're saying, is it low grade, is it intermediate grade, or is it high grade? And so these classification systems often use what we call a confusion matrix as indicated in this figure. So you're basically putting the sample or the material into a particular class so you can decide what you want to do with it. I think there's a lot of opportunity for machine learning. It's more tolerant than linear regression models, and it's less affected by particular aspects of mineralogy like nugget effects. So there's a few sensors to be considered. Each have their strengths and weaknesses. The XRF is fast. You can put it on shovels, conveyors, and it gives a quantitative elemental measurement of certain elements but not precious metals. Disadvantages, it's only actually measuring what's on the surface, so what's on the surface has to represent what's in the rock as well, and it cannot detect sulfur for bulk ore sorting. A laboratory analytical XRF can detect sulfur, but not when you have it a meter away from the material that you're trying to sense. There's too much interference from moisture and other factors. The PG&AA can measure a lot more elements than XRF, including sulfur, and it's penetrative. It penetrates through the rock to give you a composition of not only what's on the surface, but what's on the inside of the rock. It can be a little bit slow, so that means that you may not have the sorting resolution. You may not be able to sort at 100-ton scales. It might be a few hundred or 1,000 tons. It's only on belts, so you've lost some heterogeneity by the time you've transported the material to belts. The magnetic resonance, it penetrates as well. It's fast. However, there has to be an association between a particular mineral that you can detect and the precious metal that you're trying to recover. So in conclusion, precious metals usually have high levels of heterogeneity and are therefore, they have significant sorting potential. Bulk ore sorting allows selectivity while applying bulk mining methods, low-cost mining methods. The challenge is due to the ability of the sensors to measure low concentrations. There are methods, simple linear regression where you identify a proxy, multivariable regression, machine learning approaches that need to be tested and applied. And it's very ore specific. Depends on the mineralogy and the degree of heterogeneity within the deposit. Thank you for your attention.
We thank Dr. Klein for this instructive presentation and want to give him a certificate for his contributions. The The last invited speech is from Professor Shen Yang, and we invite him to the stage. The title of his speech is Fatigue Mechanical Behavior Failure Precursors and Prediction Model of Siltstones Under Cyclic Loading.
Good afternoon, everyone. I'm Shengjun Miao from the University of Science and Technology, Beijing. I'm the Dean of School of Civil and Resource Engineering. Please allow me to make a brief introduction to our school. Our school can be further traced back to the Department of Mining of Peiyang University, which was established in 1895 and is one of the earliest mining departments in Chinese history. After a long history of evolution, reorganization, in 2016, it was renamed as the School of Civil and Resource Engineering. At present, there are 5 departments in our school, which are Department of Resource Engineering, Department of Civil Engineering, Department of Safety Engineering, Department of Mineral Process Engineering, and Department of Building Environment and Energy Engineering. We have 1 lab center and 2 key laboratories. Now our school has a faculty member of 255, including 72 professors. We have now 7 undergraduate majors, which are mining engineering, civil engineering, safety engineering, mineral processing engineering, building environment and energy application engineering, intelligent mining engineering, and intelligent construction engineering. And the first 4 majors are national first-class undergraduate major and get international authentication of engineering education. In total, we have over 1,000 undergraduate students. We have over 1,400 graduate students, including over 400 PhD candidates. Among all the majors of our school, the mining engineering has been selected as a world-class discipline by Chinese central government. It means that the mining engineering is one of the best major in China and can get good financial support. Here shows the major research fields of our school, which are mainly in fields of mining engineering, civil engineering, and safety engineering. And the geology discipline is also ranked as top 1% of ESI disciplines. In terms of international cooperation, we have some platform that supports research and educations for staff members and students. We have a platform supported by the 111 project, which is the greatest international cooperation project supported by the Ministry of Education of China. And this project focuses on mining of deep underground resource. We also participate in the construction of the Research Institute of Sino-Foreign Culture Exchange in Mining and Steel Industry. And we have 3 Beijing International Science and Technology Cooperation bases on mining, engineering, and civil engineering. Now, we in total have fundings of over 50 million RMB of international cooperation, including both government-sponsored and commercial research projects. And we have joint training agreement with overseas universities, which can support undergraduate students to study abroad. We also carried out international exchange program for students. For example, we organized a one-month summer camp to Finland and Japan this year. And we look forward to cooperating and communicating with you. Thanks. And then I'd like to present some of my team's recent research on rock mechanics. I'm so sorry for changing the title. Today, my presentation topic is fatigue mechanical behavior, failure precursors, and prediction model of seal stow and cyclic loading. I will present my research in 5 parts. First, let's start with the background. In recent years, with the adjustment of Chinese economic structure, resource development has gradually shifted to Western China, such as Xinjiang province and Ningxia province. There are many weakly cemented structures, such as the Jurassic and Cretaceous in Western China. Their strength is low and cementation is poor, making it difficult to prevent and control mining disasters. Taking coal resources as an example, the 14 coal bases in Western China hold about 50% of the coal reserves, with weakly cemented structure accounting for 54%. The disasters such as rock collapse and rock burst during mining process are related to dynamic cyclic loads. The same with other rock engineering. For example, the storage and drainage process of reservoirs, the transport dynamic load is borne by railway subgrade, and so on. Therefore, it is essential to research the stability of weakly cemented rock engineering under cyclic loads. So, we conduct a series of cyclic load tests and various stress parameters. And then we review the failure mechanism and the precursors instabilities of rock from the microscopic perspective. Finally, we established a theoretical model for predicting rock failure. The concept of fatigue failure and cyclic load originated from metal materials. However, rock is a typical porous materials, and its mechanical behavior is very different from that of metal. Moreover, existing research have shown that there are significant differences in the mechanical response between hard rock with soft rock and cyclic loading. And even for the same rock shows different effects on the strengthening or weakening and cyclic load. With these questions, our team focused on seal stow in Western China and conduct a series of tests. Part 2, multi-dimensional non-uniform failure and characteristic stress of rock. First, we studied one-dimensional mechanical behaviors of seal stow. Here, one-dimensional refers to certain non-directional physical quantities, including volumetric strain, wave velocity, and acoustic emission counts. The seal stow we studied has low hardness, small particle size, and high porosity up to 20%. The initial wave velocity is only about 2,500 meters per second. And the uniaxial compression test, we found that the volumetric expansion stress of the seal stow is only 44% of the UCS, which is obviously lower than the 80% observed in dense and hard rock, such as granite, marble, and sandstone. And then we studied two-dimensional apparent non-uniform strain of siltstone. In this section, we use the three-dimensional digital image correlation technique to analyze the zone failure characteristics in the failed siltstone specimen. We divided the rock into three areas: the penetrating crack area, the broken area, and non-penetrating crack area. By comparing the stress-strain relationship in these zones, we established the localization indicators, which can describe the process of pore closure, stress redistribution, crack formation, and coalescence in siltstone. Then we analyze the special characteristics in siltstone using CT scanning and three-dimensional fracture reconstruction techniques. By calculating the three-dimensional cracks equivalent volume in the field specimen, we propose the volume proportions and fractal dimension of these three types of cracks in different regions. We found that medium-scale cracks was most critical factor influencing the complexity of rock failure mode. Based on the previous research result, we know that the cracks of siltstone show the significant multi-scale and non-uniform characteristics. The traditional characteristic stress determination methods have a certain limitation for the siltstone. Therefore, based on the CT Martin's method, we further differentiated the volumetric strain of rock into elastic solid phase strain, elastic worse strain, and plastic strain of rock into through the step cycle loading and unloading test, and establish a new method. The calculation result of the crack initiation stress and the crack damage stress of the siltstone use this new method were respectively 40% and 76% of the UCS. Part 3, strengthening, weakening, and fatigue effect of rock and cyclic loads. In this part, based on the previous characteristic stress division, we studied the influence of upper limit load and cycle numbers on the mechanical properties of siltstone. First, as shown in the test group 1, cyclic load tests were conducted and different upper limit loads. If the specimen failed during the cyclic loading process, it was called a fatigue test. If the specimen was not damaged after 3,000 cycles, then monotonic loading would be continued applied until failure occurred, which was called cyclic 2 monotonic loading test. Group 2 and Group 3 keep the upper limit load constant and change the cycle number, and then followed by monotonic loading. In Group 2 and Group 3, the upper limit loads are respectively 55 kilonewtons and 45 kilonewtons. Next, I will provide the detailed analysis on the result of this test. Firstly, based on the cyclic loading test on siltstone and different upper limit load, we found that the peak strength of siltstone showed the weakening, strengthening, kills, and fatigue effect at the increase of the upper limit load. Specifically, when the upper limit load is in the initial compacting stage, the siltstone peak strength is lower than the UCS. When the upper limit load is in the elastic deformation stage, the siltstone's peak strength is higher than the UCS. The siltstone's fatigue strength is about 88% of the UCS. when the upper limit load is between the damage stress and the fatigue strength, the siltstone's peak strength is influenced by the rock's discreteness, showing chaotic behavior. The specimen either quickly showed fatigue failures or their peak strength increased. For the upper limit load of 55 kilonewtons, it can be observed that when the cycle number is less than 300, the siltstone's peak strength is lower than the UCS. As the increase of the cycle number, the peak strength rapidly increased and then stabilized. And the results of group 3 are almost consistent with group 2. This indicates that the siltstone strength is influenced not only by the upper limit load, but also by cycle number. Moreover, cyclic loading initially caused the damage to the rock, and then continuous closure of cracks results in strengthening effect, which is a slow cumulative process. And then we use the electron microscope scanning techniques to observe the fracture morphologies of siltstone and different test conditions. We found that when the upper limit load is low, the cracks propagate along the weak structures and was compact obviously during the elastic deformation stage. And fatigue failure was caused by widespread damage and fracturing of rock, crystal, and high stress condition. Therefore, we propose the concepts of weak structure fracture effect and the comparison and embedding effects in siltstone and cyclic loading. In the first part, we studied the similarity mechanical behavior between the fatigue and the creep test. As early as 20 years ago, Chinese expert Xu Renge and former president of International Society for Rock Mechanics, Yi Brown, have found that the deformation behavior of rock and cyclic loading is controlled by the stress-strain curve of monotonic loading. In addition, both the fatigue deformation curve and creep curve of rocks show typical three-stage characteristics. Therefore, we used rheological theory to study the fatigue failure limit of rock. In this section, we focus on two key points. Point A represents the acceleration starting point of fatigue deformation, and point B represents complete fatigue failure. Next, we compare the strain and stress values between the creep and fatigue test of point A and point B. We found that the strain at point A is approximately equal to the peak strain and uniaxial compression. In other words, under cyclic load test, the limit of axial strain is the uniaxial compression peak strain. Furthermore, we found that the deformation rate and cyclic loading can reach 5,000 to 7,000 times that of the creep deformation rate, showing significant time-dependent behavior. However, regardless of how fast the fatigue deformation rate is, it is still controlled by the peak strain of the static loading test. Next, we analyze the relationship between the peak strain and the peak strength of the siltstone. From the test results with the upper limit load of 45 kilonewtons, it can be observed that the axial peak strain, the conformational peak strain, show a good linear relationship with the peak stress of siltstone after the cyclic load. In other words, with the increase of the cycle number, the siltstone's peak stress increased with the peak strain increase. Similarly, the test result of the upper limit load of the 55 kN follow the same laws. All these results indicate that the ultimate strain of the rock prevents the unlimited increase of the peak strength after cyclic loading. Part 5. Based on the previous research on fatigue limited deformation, this part mainly studied fatigue failure precursors of the rock. Here, we observed a common characteristics among this fatigue specimen, where there are volumetric compliance transition from positive to negative values. In contrast, the volumetric complex of the specimen that have not undergone fatigue failure remains consistently positive. Therefore, we can consider the transition from positive to negative of volumetric complex as an earlier precursor of rock failure, fatigue failure. This indicator can be used to determine whether the rock will failure. Next, we studied the correct growth mode of rock with AF to RA ratio of AE. We found that it fit a logarithmic linear relationship between the magnitude and frequency of AF to RA ratio. And the slope decay of this relationship can be used to express the propagation of shear cracks. And we also found a significant sudden increase in BK prior to fatigue failure occurrence. Therefore, we consider the phenomenon as the short-term precursors of fatigue failure. This indicator can be used to determine when the rock will failure. Based on the previous studies on fatigue ultimate deformation and fatigue precursors, we introduced viscoplastic damage element with stress threshold, strain limit, and damage variable. Then connect this element in series with the bogus model, resulting in a fatigue damage rheological model. Next, we saw the model and sense wave loading. The theoretical curve obtained from the model aligns well with the test result and is accurately reflects the stepwise damage evolution characteristic of rock and cyclic loading. Finally, we proposed two criteria to predict the fatigue life of the rock. The first criterion determines when rock enters the accelerated deformation stage based on the fatigue ultimate strain. The second criterion determines the duration of accelerated deformation based on the evolution of the damage variable. By combining these two criterion, we can obtain the complete fatigue deformation time of rock and predict its fatigue life. That is the end of my presentation. And I appreciate the opportunity to share my work with you. That's all. Thank you so much.
Professor, thanks again for the presentation. We will again present you your certificate and a small gift.
Okay, thank you.
So this is the end of the invited speaker sessions. The welcome and cocktail will be in the main building in Hall Eleanor, close to the lobby area. Thanks again. Açılış kokteyli salon Eleanor'da, ana binada, lobiye yakın olan salonda. Teşekkürler hocam.